When in 1938 war clouds were gathering over the continent of Europe, the Rolls-Royce factory in Derby assumed a new importance. Home of the company since its inception in 1906, it was from here that one of the United Nations' greatest contributions to victory was brought to fruition by a picked group of designers, engineers and executives under the able leadership of Sir Arthur Sitgreaves and Mr. E.W. Hydes. Inspired by the tradition handed down by the late Sir Henry Royce that only perfection was good enough, management and workers set about the task of further developing an aero engine which would enable the air forces of democracy to sweep the enemy from the skies and bomb his industries into submission. This engine was the Merlin. Away from imminent danger of air attack, an unobtrusive country house set deep in the Derbyshire countryside sheltered the Rolls-Royce Aero Planning Department. Here, engine designers worked under conditions of highest secrecy on the development of the Merlin engine, armed with data and experience gained from previous engines. The main characteristics of the new engine had already been decided in theory by the Engine Development Committee at Derby, and now began the task of calculating main dimensions and producing the plans for quantity production. At the same time, scale models of complete engines and power plants were made of wood in order to visualize and check the exterior dimensions, while much time could be saved in checking the dimensional suitability of modifications. Matters like frontal area, engine weight, working of retractable undercarriage, position of center of gravity could all be deduced from measurements and behaviors of these models. Next step was the making by skilled engineer draftsmen of many thousands of detailed working drawings, which would constitute the basis for building the prototype. As these drawings had in turn to be duplicated for use in the workshops, a blueprint department with an average output of 6,000 drawings a day was brought into being. At the experimental shop in Derby, emphasis is on the man rather than on the tool. Versatility is the keynote. Every job is different, and the men in this shop are among the most skilled workers in the Rolls-Royce organization. Soon the first components begin to take shape. In the experimental shop, the tool equipment is less specialized than that of the factories on production work, as it is concerned mainly with one-off jobs. Where duplication is necessary for parts like connecting rods, a Keller machine is used. The cutters are made to follow a master template, producing several identical pieces at a time. Few jigs and fixtures are available in the experimental stage, so the alignment of a machined surface is checked on the marking off table. A new engine is seldom built complete at first, so that although the production engine may have 12 or 24 cylinders, the first experimental job may only consist of one section of the crankshaft. And from this single-cylinder engine comes the first positive information. From these results, a forecast of the behavior of the full-size prototype can be made. When the prototype is assembled, it goes to the test house. The engine is coupled to a dynamometer, which is a form of water brake, which absorbs the entire power output of the engine and is capable of adjustment so that the characteristics of the engine at different loads and speeds can be measured. The control panel also has fuel consumption, boost pressure, oil pressure, coolant temperature, engine revs, power output, and many other quantities. Ever since it was first developed, the rated horsepower of the Merlin has steadily increased. The later types have a power output 2 or 3 times as great as that of the original prototype, without any great change in leading dimensions. After test, the prototype is stripped down and its parts are subjected to minute inspection. Parts which show signs of undue stress or wear are examined by the chief engineer and designers, who decide what alterations in design, manufacturing methods or materials are necessary. Once the prototype has passed its first test bed trials, it undergoes further tests with the air screw fitted. Finally, it is ready for its flight test. Installed in an aircraft fuselage, the Rolls-Royce test pilot takes off to confirm that the Merlin engine will in practice do as much and even more than the designers had planned. Realizing that quantity, as well as quality, would be the need of the day, the Air Ministry asked Rolls-Royce to build a large factory away from Derby for the quantity production of Merlin engines. In 1938, work began on the erection of a large ultra-modern plant at Crewe, while in 1939, as war became a certainty, the company were asked to build yet another factory about twice the size of Crewe. Glasgow was selected, and work commenced on the Glasgow plant in July 1939. By early December, the first machine tools were already in production on the Merlin. In laying out the various factories for quantity production, the problem of the most efficient placing of machines and processes was solved by making planned silhouettes to scale of each machine and item of workshop furniture. These silhouettes were then maneuvered on a scale floor plan until the ideal disposition was found. The layout was then photographed, and copies were sent to the plant engineers. As soon as all the machines were installed, full-scale production on Merlin engines commenced. Producing the Merlin engine in vast quantities without losing anything of the world-renowned Rolls-Royce qualities of precision workmanship presented untold obstacles. Apart from the difficulties of operating under wartime blackout conditions and the demands of the fighting services on road and rail transport, making difficult the movement of raw materials, there was the problem of labor. To overcome the manpower difficulty, training establishments were set up in various parts of the country. Under the tutelage of skilled Rolls-Royce craftsmen, both men and women were given intensive training in the operation of highly specialized machine tools in a section of the factory specially equipped for this purpose. In order to increase the supply of engineering draftsmen, experiments were made in training women of suitable educational qualifications. Inspired by the firm's tradition, these women eagerly proved their aptitude for this exacting work, and large numbers graduated to works drawing offices at the various plants. Apart from training men and women for aero engine production, the company was faced with the problem of housing and transporting them to and from work. At both Crewe and Glasgow, housing estates and hostels were built within sight of the plant to shelter the workers who had come from all over the United Kingdom. In view of the fact that in Glasgow alone over 1,500 houses had been built, the local transport companies were called upon to cooperate in organizing 126 special bus services to and from a depot inside the works itself, enabling the workers to get immediate transport to outlying districts. To protect the factories against air and ground attack, strong home guard and civil defense detachments were formed, made up of volunteer workers from the various plants. Fire brigades, also manned by workers, soon reached a high degree of proficiency and were equipped with motor pumps and all the latest firefighting appliances. The Rolls-Royce organization was possibly unique in having its own bomb disposal unit, equally prepared to play a vital and dangerous part in an emergency. In order to safeguard the workers' health, an efficient medical organization was brought into being. All new workers were given a medical examination and eyesight test, while surgeries and restrooms, staffed by resident doctors and nurses, were a feature of each plant. In order to ensure maximum cooperation between workers and management, joint production committees were formed at each factory, consisting of representatives of the management and representatives and shop stewards of the workers. Vast stocks of raw materials were built up, and a sample of every piece of incoming bar, tube, rod, or forging was sent to the laboratories for analysis. Each batch of material was given a number which stayed with it through every process, and a sample was taken so that a fault developing at any time during the component's history could be traced back to the raw material stage. Some of the most valuable raw materials were the light metal and other alloys discovered and developed in the company's research laboratories at Derby. Apart from the famous RR50, used in the manufacture of castings, many other equally important contributions to the Allied war effort were made by the pick of scientists and technologists working in these laboratories. In the Rolls-Royce drop forge shop, alloy steel forgings were pounded out night and day. The most highly stressed components of the Merlin engine are made from these forgings. which allow a very high output of accurately formed parts, while the metal itself, due to its molecular flow under the blows of the forge, becomes more homogeneous and capable of withstanding higher strains. In the manufacture of the Merlin engine, the light alloy foundry at Glasgow is unique in the Rolls-Royce organization and probably in the world. The foundry, with its core, moulding and fettling shops, occupies 2 entire blocks of the factory and is organized, like the rest of the plant, on a flow production basis. The layout of the foundry and its organization for production constitute a great feat of technical planning. Every kind of casting used in making Merlin engines is produced here. Very many difficulties had to be overcome on the material side of the process, and the achievement is made more remarkable by the fact that many of the workers are trainees, a large proportion of them women. Core making is a process which illustrates the way in which complex operations, normally requiring much time and a high order of skill, have been rendered rapid and certain in the hands of trainees of both sexes. The lighter cores are made by hand and mainly by women, on core tables to which ready-mixed sand is delivered by an overhead conveyor system. All the 300-odd intricate cores which go to each engine are made in the same manner. Organization has made each individual job simple. Men make the heavier cores by machine. A number of heavy cores are used in the upper half of the crankcase mold to form the bearing webs. This is one of the 2 main moulding bays, which are arranged on either side of the line of furnaces. The moulding machines are mostly of the rollover jolt type, both hydraulically and pneumatically operated and very simple to control. This mould for the upper half of the crankcase is the largest on the engine. Complete with cores and moulding box, it weighs a ton. The number of cores in the mould are an indication of the intricacy of the casting. This mould of the upper half crankcase, although the largest, is by no means the most intricate in the engine. The aluminium alloy, principally the famous RR50, is melted in gas-heated tilting furnaces adjacent to the mould conveyors. The larger moulds are poured from 2 sides simultaneously. This allows the use of ladles of manageable size and also tends towards an even temperature of metal throughout the mould. Very many and very large risers are employed to ensure sound metal in the casting. Castings are fettled in this bay with power saws and pneumatic hand tools. The first job is cutting off the runners and risers. On large castings, these are very massive, and a special type of twin-hand circular saw has been developed to do the job. The saws cut into the surplus metal from both sides so that it can be easily broken away at the end of the cut. Final fettling of the castings is done with pneumatic chisels. These cut away all the flash and webs which are not needed in the finished casting. Every casting is inspected before it goes for heat treatment. Before the castings are machined, they undergo heat treatment in this 88 feet long priest furnace. The castings are loaded onto bogies, which are pushed into the front end of the furnace. This automatically pushes out a completely heat-treated load at the other end. It has 3 heat zones, and the temperatures are automatically regulated within plus or minus 2 degrees centigrade. Very many Merlin castings are produced by die casting. Metal molds, or dies, are used in this process, which thus effects a considerable saving of time, since the same mold can be used over and over again. The die castings are taken away on the conveyor for heat treatment in the same way as sand mold castings. These die castings can be made to much finer limits than can ordinary sand castings. The surface is smoother, and because no gases are evolved in the mold, the metal is usually more homogeneous. The castings go to the machine shops for finishing. During the last few decades, amazing progress has taken place in the development of very elaborate and complex machine tools, both automatic and semi-automatic. Even in the hands of trainees or unskilled operators, these machines can and do perform the apparent miracle of producing in vast quantities the most intricate parts with the highest degree of precision. Actually, many men and women classed as unskilled or semi-skilled have become highly skilled and proficient in working a particular machine or operation, but the term is still used to distinguish them from the fully skilled Rolls-Royce operator. Operators, such as those at the Derby Works, have served a long term of apprenticeship, and schooled in the Rolls-Royce tradition have become qualified by this skill and experience to set up any machine and make the many adjustments necessary to keep it producing accurate work in the hands of trainee operators. Many of these machines have actually been developed by Rolls-Royce engineers, and such is the final simplicity of operation that although a skilled man would need vast quantities of complex drawings to make the parts by hand, these company-developed machines can be handled by comparatively inexperienced trainees while still retaining the rigid Rolls-Royce standards of precision. The crankshaft is probably the most highly stressed component of an aero engine. Over 140 separate machining operations are needed to produce the Merlin crankshaft. For these processes, a large number of special-purpose machines were developed by Rolls-Royce, including vertical and horizontal automatic lathes, deep drilling and grinding machines, and these crankshaft lapping machines. The rough crankshaft forging weighs 250 pounds. In its finished condition, the shaft weighs 108 pounds. The connecting rod is another highly stressed component of the engine, and over 160 operations are necessary to produce a completely articulated pair. After every machine operation on a Rolls-Royce component, the part is subjected to careful inspection before passing on to the next operation. Women prove themselves to be particularly adept at this exacting work. There are over 11,000 parts in a Merlin engine, and a high proportion of the smaller items are made from bar material on automatic and capstan lathes. Except for tool setting, this work is repetitive, though quite an amount of skill is needed to be a good operator. Nevertheless, the consistently high output figures on close limit work to Rolls-Royce standards achieved by trainee men and women who previously had no experience in the engineering industry is indeed a remarkable achievement. Some 90 different types and sizes of gear wheels go into the Merlin, and all must be produced to exceptionally high standards of accuracy. Accurate tooth form and perfect structure of the metal itself is vital to the smooth running of gearing. A special gear analyzer is used for measuring the tooth forms of helical gears. This apparatus traces an enlarged graph, showing any departure from the theoretically perfect form. Great care and thought were devoted to the development of valves and valve springs. Machined from forgings, the first valve forming operations are done on turret lathes and automatics. The heads and seating faces are covered with a special heat-resisting nickel-chrome alloy, applied in the flame of an oxyacetylene blow lamp. Exhaust valves are made with hollow stems and are half filled with sodium, which melts at a low temperature. When the engine is running, heat is transferred from the head of the valve to the stem by the sodium splashing up and down. Valve springs are made from coils of high tensile steel wire in a specially designed machine which coils valve springs continuously and automatically cuts them to length. After grinding and finishing, the springs are tempered in a special furnace. The journal and big ends of the Merlin run in bearings of a lead-bronze alloy. The bearing shells are made of steel into which are inserted casting tubes, secured by spinning their lower edges over in a lathe. After the shells have been preheated, the lead-bronze alloy is cast from a parametrically controlled electric induction furnace. The poured liners are then placed in a special cooling device consisting of a cylinder with jets of water spraying inwards. The rotor of the supercharger is outstanding among the light alloy components of the engine. This component may be called upon to run at between 20,000 and 30,000 revolutions per minute, corresponding to a peripheral speed exceeding the velocity of sound. It is therefore in the highest degree important that this rotor should be perfectly balanced. This is achieved by machining it all over. There are countless machining and finishing operations involved in the manufacture of thousands of other Merlin engine components. To each of these, unstinting thought and care were given in devising machines and machine tools capable of producing the required rate of quantity output without losing anything of the traditional Rolls-Royce quality. In order to ensure that the standards of manufacture were being maintained, Rolls-Royce engineers developed many high-precision measuring gauges and other complicated items of inspection apparatus to augment and improve the standards of normal engineering precision gauges. Inspection of each of the 11,000 Merlin components, not once but many times, was continuous throughout every stage of manufacture, including a thorough final inspection when the parts were completed. Every factory has at least one air-conditioned, temperature-controlled standards room, in which the gauges and inspection devices used in the manufacture of Rolls-Royce engines are continually checked against standard gauges and precision comparators whose accuracy is of the order of 10/1000th of an inch. When the finished components reach the sub-assembly stage, the engine begins to take shape. The assembly process is arranged as a sequence of operations in the same way as the machining. The sub-assembly benches are arranged in lines between the finished parts stores and the engine erection lines. The component travels along the assembly line through the hands of dozens of different workers who each add their part or do their particular operation so that the component is finished at the end of the line. Components like the supercharger are built up separately so that they go into the engine as complete units. At the end of the sub-assembly lines is the engine assembly shop, where the sub-assemblies are delivered at convenient points and are put together to make complete engines. Engine assembly starts with the crankcase, which has had all its studs and cylinder holding down bolts fitted on the sub-assembly benches. The engine assembly line has a bench-height rail track down the center, which enables the work to be pushed easily from station to station along the line. A turntable in the track at each siding enables the engine to be run off the main line while fitting is in progress, leaving the main line free for the flow of work. At each station, a sub-assembly or component is added to the engine. As the engine passes down the line, it gradually takes form. The policy of specialization is applied here in the same way as in the other departments of manufacture. Each job is done by a crew who are specialists in fitting their particular component. This policy enables the workers to become expert in a short time. At the end of the line, the completed engine is vetted by an inspector who notes the numbers of individual components and assigns a new number to the whole engine. From now on, it has an identity. It is given a logbook in which all its subsequent history will be recorded, but meanwhile it is to be taken away for its first run on the test bed. Every Merlin is run on the test bed before it is passed into service. The Ministry of Aircraft Production prescribe very stringent tests for engines to be used in the RAF or the Fleet Air Arm, so several hours run at the rated horsepower of the engine are followed by bursts at maximum power, while test engineers make careful notes of the engine's behavior. A certain proportion of engines which have satisfactorily passed their tests are nevertheless brought back and immediately stripped down. The running test demonstrates that every component is capable of doing its job. This strip down is to make sure that there has been no overheating or overloading, and to ensure, in short, that the engine will go on doing its job and maintain the standard of manufacture. Once more reassembled, the engines are ready for active service, but the job is not yet finished. Just before the war, it became apparent that in order to ensure the satisfactory installation of the engine and the consequent safety of the aeroplane's crew, it was necessary for Rolls-Royce to devote their engineering skill to designing the completely cowled power plant installation, ready for attachment to the aeroplane fuselage. This enterprise in tackling the complete power plant and developing it into a quickly detachable and interchangeable unit was acclaimed as one of the outstanding achievements of British aviation during the war. No survey of Rolls-Royce wartime service would be complete without reference to some of their many other contributions to the success of the Allied nations. Early in the war, it became obvious that the facilities which had been envisaged for the repair of damaged engines were going to prove entirely inadequate. and measures to remedy the position became of the utmost urgency. Rolls-Royce set about tackling this problem and had the satisfaction of seeing the figure of overhauled engines, which stood at a few hundred in 1939, rise to over 18,000 during 1944. The Rolls-Royce School of Instruction at Derby had trained nearly 17,000 people in the use and maintenance of Rolls-Royce engines and other products. Those trained included pilots, flight engineers and ground personnel of not only the Royal Air Force and the Fleet Air Arm, but of representatives of the air forces of most of our allies. Another interesting example of Rolls-Royce versatility was the development of a small caliber 40mm quick-firing gun for use in MTBs and similar craft. The Merlin engine was also adapted for powering these high-speed motorboats. Then again, there was developed a modified and unsupercharged version of the Merlin known as the Meteor, which was used to power the first prototype of a new tank. The effect of the extra power of the engine on the prototype tank was such that Rolls-Royce engineers were asked to collaborate in developing the tank itself. The fruits of this collaboration resulted in the famous Cromwell tank, which covered itself in glory on the dash from the Normandy beachheads to the Rhine. The Rolls-Royce organization may well be proud of its contribution to victory. Workers, designers, engineers, management, all fulfilled a vital role in Britain's days of need. Now they can once more turn their hands and their brains to the fulfillment of the needs of a world at peace. And this, indeed, they have done. For in October 1945, 2 months after the end of hostilities, it was a Rolls-Royce jet turbine that streaked across Britain's lowering skies to claim the world speed record of 606 miles an hour. What promises to civil aviation did this imply? What even newer principles of engine design and propulsion are now occupying the minds of the Rolls-Royce organization? For the world of science has much in store, and in the forefront of mankind's march onward will be Rolls-Royce applying to practice the newest and latest principles of scientific achievement.